introduction to Fourier series, in which we have learned about the type of Fourier series. Okay, we have three types of Fourier series. The first two are trigonometric type, okay, and then we have a complex exponential type of Fourier series. And also we did learn about the spectrum, yeah, in which there are two types of spectrum, one-sided and also two-sided, in which these spectrum are related to trigonometric cosine and also complex exponential representation respectively, yeah. Okay, so for today we're going to proceed with these topics of Parseval's theorem. Okay, basically there are two topics in lecture 8, but I'm going to cover only the second part, which is on Parseval's theorem. And for the effect of symmetry on the Fourier coefficients, I believe that you can learn this on your own. Yeah, because it's just on this effect on the symmetrical nature of the signal, yeah, and what should be the effect on the Fourier coefficient. So I'm not going to cover on this. Yeah, so please read this on your own. Okay, so I'm going to go straight to the Parseval's theorem. Okay, Parseval's theorem will be on this. You will start with the understanding on the concept of energy and power. Okay, so for us to proceed with the Parseval's theorem, we have to first understand the energy and power concept. Yeah. Okay, so in this slides, I'm going to explain about the concepts of energy and power. So looking at these equations that we have here, the first one is the energy equation. So energy equation is defined to be integrations from negative infinite to positive infinite of the Vt squared dt. Okay, so this is the equation that is used to calculate the energy of the given signal of Vt, yeah? So based on this equation, there are two scenarios that we can think about. The first scenarios is when we have a signals of Vt, in which as the time approaching infinite, the amplitude of V2 will be approaching 0. Okay, so this is the first case. Yeah? The first case is when we have a signals of Vt. Okay, we have a signals of Vt in which the Vt amplitude is said to be approaching 0 as time goes to infinite. Okay, so for this equation, I mean for these signals, for this type of signals, we can deduce that the energy for this particular signals, in which the amplitude is said to be converging to 0, yeah, we can see that the energy for this type of signals is finite. Yeah, means that we can calculate the energy for this particular signals. But for the second case, in which if we have signals that if t goes to infinite, yeah, if t goes to infinite, the amplitude will not go to 0. Okay, this is second type of signals. Yeah, the first type is that as t approaching 0, the amplitude goes to 0. But for the second type of signal, as t approaching infinite, the amplitude does not goes to 0. Okay, this is the case whereby if we integrate, yeah, if we integrate these equations of Vt squared dt for the second type of signal, we can see that the energy that shall be calculated by this equation will be infinite. Yeah, will be infinite. So it is not that I can say that there is no such case where the energy is infinite, right? So for that particular case, we are going to use another method of measuring the energy, in which we are going to use terms of power, yeah, in which power is defined to be a time average, yeah, a time average of the energy. So this will be more meaningful measures, as mentioned here, to calculate the energy for the case of the signals which is not approaching 0 in terms of this amplitude. Okay, so that should be the another parameters that will be used, which is a power, and the power is defined to be same as with above in terms of the integration, but the range of integration is from 0 to t, which is integrations from one period. Okay, okay, and we have 1 over t, 1 over the period, and the limit of t approaching infinite. So this is the equations that define the calculation of power. Yeah? Okay, so to relate this with what we are looking, what we are learning right now, in which we are learning about the Fourier series, right? So we know that for a Fourier series, the signals is periodic. Yeah. So if the series is periodic, we can see that the energy, the energy for this particular periodic signal, if we base on the equations in the previous slide, the energy that will be calculated by using the equation will be infinite. Okay, so that particular case, for a periodic signals, we are going to measure the signal strength by a power parameters, not energy. Yeah, by power parameters. Okay, so this is where Mr. Parseval, Mr. Parseval is a scientist, mathematician. Yeah, he come out with the theorem, which is called a Parseval's theorem. Okay, in which a Parseval's theorem is used to calculate the average power. Yeah, so Parseval's theorem is a theorem which is used to calculate the average power for any periodic signals, and Mr. Parseval find out that the average power for any periodic signals can be calculated by just using its Fourier coefficients value. Yeah, so the average power can be calculated by using the Fourier coefficients value. So this is the outcomes made by Mr. Parseval, in his theorem. Okay, so that's why from his theorem, he said that the average power for one period is written to be looked like this. The average power is 1 over t integrations over one period of dt squared dt. Okay, so for that case, there are two formulations to calculate the average power, in which the first equations here is for the case of Fourier series for the third type, which is a complex exponential. Remember, we have learned that for the complex exponential, the Fourier coefficients is given by Cn, right? Cn. So for that case, the average power will be calculated as summation of the Cn squared. The summation of the Cn squared. So that should be the first formulation to calculate the average power based on the application of Fourier coefficients. And if your Fourier series is written in terms of trigonometric cosine form, okay, so the average power can then be calculated based on this equation, in which we have P average is A naught squared. What is A naught? A naught is a DC value, which is without the frequencies component, DC value, plus half of summation and from 1 to infinite of the rest of An squared. Okay, so these are the formulations that shall be used in calculating the average power of the given signals, in which if you want to calculate the average power, first thing that you have to know is the coefficients of the said Fourier series terms. Okay, so these are the things that shall be understood in Parseval's theorem concept. Okay, let's have a look at this example to test our understanding on the Parseval's theorem. So we are given a complex Fourier coefficients. We are given the signals which is in the form of rectangular functions, square wave functions, having a amplitude from negative m to positive m, and the period of these signals is t naught based on this signal given in the figure here. Number one, we need to derive what is the complex Fourier coefficients for the given signal. Okay, so that should be the first one. Okay, so for the first case here, in order for us to derive the Fourier coefficients, the complex Fourier coefficients, you have to go back to the table, Fourier coefficients table, okay, in which we have learned this in the previous lecture, table B3. Okay, so you have to choose from the list, which signal that similar to the given signals here in this slide, and then from that signals you have to extract the information of the Cn terms. Okay, so that's the first thing to be done. Number two, once you have obtained the Fourier coefficients, you have to plot the frequency and the phase spectrum. You have to plot the frequency and the phase spectrum For the first 4 terms, yeah, of these Fourier coefficients, okay, that can be done, the first 4 terms. And finally, you have to calculate the average power expression for the signal. Okay, so the questions are interrelated with each other, yeah, right? Number 1, find the coefficients based on the table. Number 2, plot the spectrum, both amplitude and the phase. And number 3, need to obtain the average power based on the Parseval's theorem. So you need to use the values of Fourier coefficients from the first questions. Okay, so let's have a look at the solutions for this example. Okay, so this is the one. For these questions, we know that the x naught should be equals to Vm. Yeah? So this is when we compare the table signals with the given question. So we can say that the x naught, which is the amplitude of the signal, will be the Vm, while the period is the t naught. And by referring to table B3, you can refer to the table on your own. The signals that shall be used is number 1, yeah, which is the square wave function, in which if we extract information from the square wave function, we are going to get the C naught will be equals to 0, okay, and the Cn will be equals to negative j 2 x naught over n pi, in which x naught is the amplitude, and the Cn that we have here is only applicable for odd value of n. It means that for the even value of n, the Cn is, or the Cn is 0, yeah, for the even value of n. Okay, so based on that, we can write that this xt, or the equation of Fourier series, based on these Cn's, will be summations from n to negative infinite to positive infinite, Cn of exponential j and omega naught t. Okay, and we can write further that the omega naught shall be equals to 2 pi over t. Okay, that's understood, 2 pi over t. And we can further expand this summation to be look like this. Remember, the question asks us about the 4 since we have the Cn is only applicable for the odd value. So we need to start from negative 3, n equals to negative 3, followed by negative 1, positive 1, and positive 3. So that should be the first 4 terms, yeah, of this Cn. So we have here is for n equals to negative 3. So substitute n of negative 3 in this equation. So we have this. Okay, see that we have substitute the x naught to be the Vm. Okay, and followed by the case of n equals to negative 1, n equals to 1, and n equals to 3. Okay, so that should be the first 4 terms of this Fourier series. Okay, and afterwards, by simplifying these terms here, and by substituting j as exponential j pi over 2, so we're going to have these equations. Yeah, right. So I believe that you have understand this from what we have learned previously in lecture 7. Yeah, so it won't create much problems here, hopefully. Okay, and from here we can straight away sketch the spectrum. This is the first one, yeah. This is the first question, which is to obtain the coefficients. Yeah, so the coefficients given here, right? Which is 2 Vm over 3 pi, 2 Vm over pi, 2 Vm over pi, and 2 Vm over 3 pi. So these are the first 4 non-zero Fourier coefficients, yeah. And based on that, we can sketch the spectrum. Yeah, we can sketch the spectrum based on the frequencies value. So there should be 4 frequencies value here, starting from negative 6 pi over t naught up to positive 6 pi over t naught. Yeah, so for that, we're going to have this amplitude spectrum with respective amplitude value. And also remember that we have the phase. For instance, let's say for negative 6 pi over t naught, your phase is pi over 2. Yeah, for and the rest will follow. So end up, the phase spectrum should be looked like this. So this is your phase spectrum, and it should be the amplitude spectrum, which is obtained from the equation of xt, which is obtained previously. Yeah, so I hope that should be no problem to you, because we have learned this intensively in the lecture 7 before. Yeah, okay, hopefully that should be okay. And following this, this is where the average power comes in. Yeah. So we know that these are the amplitude of these, the spectrum, the Fourier coefficients, the amplitude of it. Okay, so to calculate the average power, we need to use these amplitude values. Okay, so since we have two values which are same, yeah, 2 Vm over pi, so straight away we can say that the average power will be summation of n of Cn squared from negative infinite to positive infinite. But since we have only 4 terms, 4 non-zero terms, so we just use 4 terms here to calculate the average power. You cannot calculate from negative infinite to positive infinite, yeah? We just calculate the average power based on the values of the amplitude that we have. So we have 4 amplitudes there. So just use the summations to calculate the average power of this xt signal. Okay, so hopefully it's clear. Yeah? So the power should be in units of watt. Okay. Let's have a look at this example here. We are given a VT signal, which is equals to 4. Yeah, 4 plus summation of n from negative infinite to positive infinite of Cn, exponential Jn 200 pi t. This is for n not equals to 0. Yeah. Okay, in which the Cn is given to be negative 8 over n pi squared. And based on this, further on given that for all even value of n, the Cn is 0. Yeah. Okay, so it means that the Cn that we have here is only valid for odd value of n. Right, so based on this, we need to write the complex exponential Fourier series expression for Vt up to the third harmonics. Okay, so it's nothing much here, it's just an expansion of the equation and substituting the Cn into this and expand it up to the third harmonics means that the summation must be starting from negative 3. Yeah, negative 3, then followed by negative 1. So we have 4 here, which is for n equal to 0, and then followed by n equals to 1, and finally n equals to 3. Yeah, that should be up to the third harmonics, yeah? Because there should be no value of Cn for even value. Okay, so once we have that, we can straight away calculate the average power based on the values of the Cn that we have obtained previously in part 1. Okay, so hopefully you understand about the flow of calculating the average power. Yeah, the first thing that you have to do is need to calculate the Fourier coefficients. Then only you can calculate the average power. Okay, so let's have a look at the solutions for this example. I think you have ideas in your mind, but never mind. I just proceed with solutions. Okay, that should be the case. So we given this equation for the Vt, okay, 4 plus summation of this Cn terms, okay, and then given this Cn and Cn equal to 0 for the even n, yeah, right. So up to the third harmonics, as what I mentioned before, this will be the expansion of the Vt, series of Vt, starting from n equals to negative 3, followed by n equals to negative 1, that should be 0, n equals to 0, yeah, which is 4. And then we have the expression for n equals to 1, and finally expression for n equals to 3. So that should be the expansion of the Vt signal. And subsequently, we can have this equation, which is based on the simplification of the above terms here. So we have this equation of the Vt in a complex exponential terms up to the third harmonics. Yeah, that should be the answer for the first question. And followed by that, we are requested to calculate the average power of Vt. Okay, so similarly, we are going to use this equation because we are dealing with the complex exponential. So for complex exponential, this should be the equation to be used. Yeah, remember there are two equations, right, to calculate the average power. The first one is for the case of complex exponential, in which this will be the equation. And if you are facing a problems in which the Fourier series is written in trigonometric cosine, so that should be the second equation that shall be used. If you can remember, you can recall back, the equation is P average equals to A naught squared plus half summation of A n squared. Okay, so there are two options to calculate the average power depending on your Fourier series. form. Yeah. Okay, so based on this, there are these are the Fourier coefficients. Yeah. So simply we can just write the average power should be equal to this equation. I think I missed something here. I forgot to include 4 here. So 4 should be there. 4 should be included here. Sorry for that. I forgot to put 4. So by right, it should be 2 of negative 8 over 9 pi squared plus 2 negative 8 over pi squared plus 4 squared. Yeah, need to include 4 also. Yeah, because this is summation of Cn for all n, yeah, including n equals to 0. So you need to add with 4 squared, yeah, in the average power. Sorry, I missed the 4 squared in this equation then. Okay, any question on the average power so far? No? Okay, if there's no questions, the question? Is there any questions? Yeah.
Yeah. The example one.
Yeah.
It said that number 2 plot the frequency, not the amplitude.
It's supposed to be amplitude, sorry.
Oh,
It's
okay.
supposed to be amplitude, yeah?
And the complex Fourier series coefficient, I think
Mm-hmm.
it's rectangular based on the table it shows, isn't it?
The table will give you the complex Fourier coefficients. It should be the Cn.
Yeah, yeah. But I think it's look like rectangular, not square, isn't it?
For that table,
Hmm.
let me see, yeah? Right. Sorry for that. Oh, this is the one, yeah, that you mentioned to me. Square wave, is it?
Yeah.
Yeah, it should be the one. This should be the one.
Why?
Why?
Oh,
Why this one?
yes.
Okay, so compare the signals here with the one that you have in the problems. Okay, let me... Okay, the one that we have here in the problems look like this. Okay, this is the one. Okay, so if you compare the table signal with this, is there a difference between them?
I think the square wave is look more square, isn't it?
Look more square, maybe because of the illustration problem, supposedly.
So it means that the square wave got reaching the positive and negative amplitude, isn't it?
Okay, so we have negative and positive amplitude.
So it means that the wave is square wave. Is it?
The wave is square. Let me
Compared
see.
to the rectangular wave, I think it's look very similar.
Let me see, yeah. Okay. Is there any case that, okay, we compare the first and the six signals here, right? Okay, the square wave do have the positive and the negative amplitude. For this 6 wave, it is only have a value from 0 to positive. Okay, so if we compare the problem that we are given in the case, the example that we have here, is it mimic the first or the 6th wave there?
Okay, I understand.
Okay, thank you very much. Yeah? That should be the first wave. So you have to compare it wisely between the problems and the signals given in the list. Yeah. Okay. Any more questions for this example? No, it's no questions. So we're going to proceed further with